Hello everyone, this is Samarth. So I'm here to demonstrate Huffman coding. Huffman coding, as we know that it is a file compression technique which is usually used in file compression formats like zip and JPEG. It is a lossless data compression technique which is a very efficient technique when compared to other traditional or conventional encoding techniques like binary encoding and all. So let's start. So in this technique, we have mainly 5 steps, which is creating frequency table of the characters, initializing priority queue for arranging them in ascending order of the frequencies. Next, we are going to build the tree with the frequency table by grouping the frequencies in increasing order. Next, we are going to assign some codes like 0 for the left subtree and 1 for the right subtree of the resulting Huffman tree that we are going to create. And lastly, we are going to calculate the total number of bits required to encode a message. So let's start with the input text as Sam Altman. So in the first step, we need to create the frequency table. Over here we can see that a frequency table is created where S frequency is 1, A frequency is 3, M frequency is 2, L frequency is 1, T frequency is 1, and again N frequency is 1. So this is the first step where we are going to create a frequency table of the input string for all the characters that appear in that particular string. So in this second step, we are going to initialize a priority queue for arranging these frequencies in ascending order. So in order to reduce the conflict of same frequencies, as we can see in this case, like S, L, T, and N are having same frequencies. So in order to resolve this conflict, we are just going to arrange the frequencies of the letters as they appear in the string, like in a sequential manner. So let's go to this step. Yeah, over here we can see that priority queue is created with the ascending order of the frequencies. Since all these are having the frequency of 1, they are arranged as per they appear in the string. Like L appears first after S, T appears after L, and N appears after T. So this is how we resolve the conflict of same frequencies, followed by the increasing number of frequency, which is M and A, with the frequency of 2 and 3 respectively. So let's now start building the tree from this frequency table. So in the initial stages, the lowest frequencies that we can observe over here is 1 and 1 of S and L respectively. So we'll club that together and we'll create a node which will contain the sum of these frequencies, which is 2. Again, let's search for the next two lowest frequencies in the table. The next two lowest frequencies are again 1 and 1 of T and N respectively. So we'll group them together. So now we have 2 and 2 nodes, two nodes of value 2 each. So now we need to compare these frequencies with the created nodes, which are the resultant of grouping of these 4 nodes. So over here we can see that M is also having a value or frequency of 2. Now let's combine or group this with the first node of 2. And next, after grouping this, the resultant will be grouped with A frequency with the node created by clubbing of N and M. So this is how we'll group these together and form a Huffman tree. So this is a final Huffman tree structure. So over here we can see that in the initial stages, S and L, which were initial frequencies, initial lowest frequencies to be precise, were grouped first. In the next step, T and N, which were again having the frequency of 1 and 1, so they were grouped in the second stage. Next, the frequency with of M, which was 2, is grouped with the first grouping of S and L. One more thing we need to keep in mind while grouping is if the frequency of the new node which is going to be grouped is less than the already grouped frequency, then we are going to place it to the left of the node. In this case, we can see that both are having same frequencies, so it will be placed to the left. So the conditions for placing the frequency or the letter at the left is they should be either less than or equal to the frequency of the node with which they are going to be combined. And in this case, as we can see that the frequency of A is 3 and the value of this node, which is created by the grouping of frequencies of T and N, is 2. Since 3 is greater than 2, it is placed to the right of this node. So this is how we are going to combine two like frequency of A with T and N. So the resultant node is 5 by the sum of 2 and 3, and over here it's 2 plus 2 4. And finally when we combine these two or group these two with 4 and 5, we get a root node of value 9. So as per the rule, we need to assign the left subtree with the value of 0. As we can see that the left subtrees are assigned with 0 and the right subtrees are assigned with the value of 1. So over here we can see that the right subtree is assigned with the value of 1. So with this tree we are going to generate codes. So for code for the yum will be 0 and 0. The code generation actually happens by the traversal from the root node to the leaf node. So in order to generate code for yum, it will be from uh, ninth node to yum node. So the code for this will be 0 0. And if we similarly, if we want to generate code for yes, it will be 0 1 0. Similarly for L, it will be 0 1 1. And for T, it will be 1 0 0. N, it will be 1 0 1. And for A, it will be 1 1. So as we can see that we are going to generate codes. Over here we can see that it has generated codes as I mentioned earlier. So now we are going to calculate total number of bits which are required to calculate the to encode the bits. So the total number of encoded bits for the text is 22, and for in order to for encoding it's 12 bits, but in order to transfer the message we need to also add the data of this frequency table. So we are going to add this to the number of bits encoded, which is 64. The total number of bits now required for transferring this input string message is 86 bits. So this is how the Huffman coding works. So thank you.
Hello, my name is Abhilash and today I am going to explain Finite Automata string matching algorithm. This algorithm is used to find whether a pattern exists inside a given text. Instead of checking characters again and again like naive method, Finite Automata uses a pre-computed transition table to make matching faster. The basic idea comes from the concept of finite automata, which is machine with different states. Each state represents how many characters of the pattern have currently matched. For example, if a pattern is ABAB, then state 0 means no characters, state A means A is matched, state 2 means B is matched, state 3 means A is matched, and state 4 means B is matched. And state 4 will be the final state. Before searching, we build a transition table. This table tells us that if we are currently in a certain state and read a particular character, what would the next state be? While scanning the text, if character continues matching, we move forward through the states. If a mismatch occurs, the automaton automatically jumps to the correct state instead of starting over. When we reach final state, it means the complete pattern has been found in the text. The main advantage of this algorithm is that searching becomes very efficient because each text character is processed only once after pre-processing. Its time complexity is for pre-processing big O of m into alphabet size and for searching big O of n, where m is the length of pattern and n is the length of text. Let me show you an example on this later. We have a text string and we have a pattern ABAB. Since the size of a pattern is 4, we will have 4 plus 1 states. And here we have a transition function table. First input will be A. The transition is from 0 to 1. Next is B. Transition is from 1 to 2. Next is C. The transition will be from 2 to 0 because the pattern is not matched. And next input is D. For input D, it will loop on to its original state. Next we have input as E, and for in and for input E also the state will remain same. Next we have A, it goes from 0 to 1. Next we have B, it goes from 1 to 2. And next we have C, since the pattern is not matched, it goes from 2 to 0. Next we have D, it remains in the same state. Next we have E, it remains in the same state. Next input is A, it again goes from 0 to 1. Next is B, it goes from 1 to 2. Next is A, it goes from 2 to 3. Next is B, it goes it goes from 3 to 4. And we have reached the final state. It means that we have found one match, and the match is at index 13. And now we continue with the character C as an input. It goes from 4 to 0. Next input is A. It goes from 0 to 1. And since the text is all scanned, we stop here. We can see that we have found a match at an index 13. Now, for the application part, this algorithm is commonly used in text editors, compilers, and search systems. Thank you.
Hashing is a collision resolution technique used in hash tables. A hash table stores data using a hash function that converts a value into an index. So the basic hash function is given as hash function is equals to key mod table size. The problem occurs when two values generate the same index. This situation is called a collision. To resolve collision, we use double hashing. So in double hashing, instead of checking the next slot sequentially like linear probing, we use another hash function to calculate the jump size. So the probing formula is given as index is equal to hash function 1 plus I into hash function 2 mod table size, where I is the probe number. So this helps reduce clustering and distributes values more uniformly. Now let us see how this works using the simulator. On the left hand side, we can insert the numbers and see the detailed calculation steps. On the right hand side, we can see the actual hash table. The hash table here is 11, which is a prime number. So prime numbers are preferred in double hashing because they help the probing sequence cover the entire table efficiently. So now I will insert the value 27. So as you can see that the 27 occupies the index 5. Since the index 5 was empty, the value 27 is inserted directly. So we can now see that the 27 is stored at index 5 in the hash table. Now let me insert 12. So we can see that it is performing the calculation, and we can see that the index 1 is empty. So the 12 is inserted successfully at the index 1. Now let me try inserting 24. So we can see that the insertion is successful, and index 2 was empty. So the 24 is inserted in the index number 2. So now let me try inserting 12. So as you can see that the 12 had collisions. So when we calculated the hash function 1, so we got the answer as 1, but the index 1 is already occupied. So a collision occurs. So now the secondary hash function is used. So when we calculate the secondary hash function, we get the value as 2. So the step size becomes 2. So now we calculate the next index using the double hashing. So we use the double hashing formula. So the new index comes out to be 3. So index 3 is empty, so the value is inserted in the third empty index. This demonstrates how double hashing resolves collision efficiently. Thank you.
Good morning everyone. Today I am going to explain KMP algorithm, which stands for the Knuth-Morris-Pratt algorithm. It is an efficient string matching algorithm used to find the pattern inside the text. The main advantages of KMP is that avoid the unnecessary comparison and work faster than the normal string matching method. A string matching means searching whether a pattern exists inside the larger text. Our goal is find the position of the pattern in the text. Problem with the navy algorithm is in the normal or a navy string matched method, whenever a mismatch occurs, the comparison starts again from the beginning of the pattern. This causes repeatedly comparison and increases execution time. The repeated checking happens many times, hence the time complexity will be big of n into m, where n is length of text, m is length of pattern. Here, KMP algorithm solves this problem by using the previously matched character. Instead of restarting comparison from the zero, it intelligently shifts the pattern using a pre-processing array called the LPS array. The LPS stands longest proper prefix, which is also suffix. It tells how many characters can still be reused after a mismatch occurs. Taking an example, we are entering a string. The string is ABX, ABC and ABC, ABY. Here we need to find ABC, ABY. We need to calculate the LPS table. We need to find the prefix and suffix values. Here A have no prefix and suffix, hence it is 0, and AB have A is prefix, B is suffix, there will be no matching, hence it is 0. And a string is ABC, a prefix is A and AB, the suffix is B, C, C, there will be no matching, hence it is 0. The string is ABCA, the prefix of this A, AB, ABC, then the suffix is BCA, CA, A. Then there is a common A, but then the length is 1, hence it is A is 1. The next string is ABCAB, the prefix will be A, AB, ABC, ABC, A. Then the suffix is BCB, CAB, AB, B. There will be the common AB. Then the length is 2, and hence it is B is updated to 2. Then the string is ABCABY. This prefix is A, AB, ABC, ABCA, ABCAB, and the suffix is BCABY, CABY, ABY, BY. There is no common in between, hence it is 0. And the index starts from 0, 1, 2, 3, 4 and 5. We computed the LPS table. Next we have to check the text and the pattern value, it is found or not. We need to find the text equals to P of I. How this works? The T of I equals to P of I. Here example, T of I equals to P of I, A equals to A, it is matched. It is incremented by 1. T of 2 equals to P of 2, B equals to B is also matched. Next, text of 3 equals to P of 3, X is not equals to C, hence it is not matched. Then the P of 3 will be decremented by 1. The P of 2 plus 1 is P of Z. Here will be the P P of value will be 1. T of 3 equals to P of 1. Hence it is also not matched. Hence the text will be the incremented. T of 4 equals to P of 1. That is A equals to A. It is matched. Next, text and pattern will be incremented. T of 5 equals to P of 2. The B equals to B. They are also matched. Again, T of 6 equals to P of 3. C equals to C is also matched. T of 7 equals to P of 4. A equals to A is also matched. T of 7 equals to P of 4 equals to A equals to A is matched. T of 8 equals to P of 5. B equals to B is also matched. T of 9 equals to P of 6. C is not equals to Y. Hence we decrement the pattern P of 5 plus 1 equals to P of Z. The P of Z will be the 3 and the T of 9 equals to P of 3. Hence C is equals to C. T of 10 equals to P of 4. It is also matched. T of 11 equals to P of 5. B equals to B is also matched. T of 12 equals to P of 6 is Y equals to Y is also matched. Hence the pattern will be found.